Let's start our lecture on Chapter 2. An element is a pure substance that cannot be broken down into simpler substances via chemical reaction. In other words, it's kind of like the smallest building block of matter that we can use to make compounds and make all sorts of stuff that we see around us. Now, each element is identified by a 1 or 2 letter symbol. Okay? Now, you need to make sure that you do this correctly. With these symbols, the first letter is always capital, so capital N. The second letter is always lowercase, so lowercase a. This would be sodium. Now, this, capital N, in a capital A, even though it's smaller, that is still a capitalized A. This has a different meaning to us. In chemistry, this is what we would call Avogadro's number. These two things are not equal. Okay? Now, elements are arranged on the periodic table. The periodic table was discovered by Dmitry Mendeleev, a Russian chemist, who basically what he did was he took all of the known elements of his time and put on note cards all of their different properties, like their mass, their color, their density, things like that. And he arranged them and rearranged them, and he found a pattern, what we now call the law of periodicity. And it's this position on this periodic table that tells us a lot about the chemical properties of each element. So here we have a table of common elements. You might notice that some of these elements don't seem to have a set of symbols that fits with their name. Copper, Cu, there's no U in copper. Lead is Pb, and potassium's K, and sodium's Na. How does that work? Well, these are from the Latin names, okay? Copper was cuprum, lead was plumbum, potassium was kalium, and sodium was natrium. So some of these don't exactly look alike. Beware of those that have different symbols than their name sounds like they should. Now here is a modern periodic table. Okay, it is arranged using these numbers up at the top. You see the 1, 3, 4, 2, 5, 6, 7, etc. That is what we would call the atomic number. And we'll see how the atomic number is determined in just a few minutes. But it's arranged in increasing atomic number. Now, there's a lot more to the organization of this periodic table that you should know. The columns here are called families or groups. The rows here are called periods. Okay? So the families are groups, and then the periods. You also can tell that we've got these green, these brown, and these blue element boxes. These are the metals, the metalloids, and the nonmetals. You can see that the metals are on the left side of the periodic table, and they actually comprise most of the periodic table. Most elements are metallic in nature. The blue boxes, the nonmetals, are on the right side of the periodic table, and the metalloids follow this staircase that's in here, and they're on either side of that staircase. Okay? So the only two that are exceptions are aluminum and polonium. Those guys are metals. Okay? Now, there are a bunch of elements that I want you to memorize the name and symbol for. Okay? Just the name and symbol. Now, I'm going to underline these guys in red. Okay? And say their names as I go through them. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, bromine, krypton, rubidium, strontium, silver, cadmium, indium, tin, iodine, xenon, barium, platinum, gold, mercury, lead, radon. These are the elements I expect you to know the name and symbol for. Okay? It's a little less than half of the periodic table. Okay? But it's very important that you are able to recognize these because these are the most common elements that you're going to run into. There are a couple that are not necessarily as common that I'm having you memorize, but they're going to come in to play when we start doing chemical nomenclature or naming of chemical compounds. So it's important that you memorize them. So elements in the periodic table: metals, nonmetals, metalloids. What are these things like? Metals, as we said, are on the left side of the periodic table. They're good conductors of heat and electricity. They heat up really well, they conduct electricity. They're shiny solids at room temperature, except for mercury, which is a liquid. Metals are also malleable and ductile. Malleable means if you hit it with a hammer, it deforms. I always remember malleable with mallet. Mallet is another word for hammer. Malleable, if you hit it with a hammer, it turns into a sheet. And ductile means you can stretch it out and turn it into wires, like ducts. So you can hit with a hammer, and you can stretch them out. Nonmetals are the opposite of metals. These are on the right side of the periodic table, and they are dull. They are not shiny. If you hit nonmetals, solid nonmetals with a hammer, they're going to break. These are what we call brittle. They are poor conductors of heat and electricity. And nonmetals can be solids, liquids, or gases at room temperature. Now, there's only one liquid nonmetal, and that is bromine. Metalloids are on that solid staircase that starts at boron and goes down to astatine. Now, metalloids have intermediate properties between metals and nonmetals. Some are shiny, some are dull, they're not good conductors of heat or electricity. They're not poor conductors. They're semiconductors. You may have heard of silicon as a semiconductor. So there are only 7 elements that are metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. Compounds are formed when we take 2 elements and we chemically combine them together. Okay? 2 or more elements, I should say. And a chemical formula is going to consist of the element symbols that we're going to use to show the identity of the atoms present in the compound. We also show the ratio of atoms in the compound using subscripts to show us the number. So let's take H2O. Everybody knows water. This means that there are 2 atoms of hydrogen, every 1 atom of oxygen. Now, here we have Hank Hill's favorite, propane, C3H8. This means that there are 3 carbon atoms and 8 hydrogen atoms. Now, what if I have something like NaCl, good old table salt, sodium chloride? If I don't have any subscripts, then what that is implying is that there's just 1 of each, 1 Na to 1 Cl. Now, chemical formulas are great for a shorthand of writing down what we have present, but we can visualize atoms and molecules in so many different ways. And probably one of the hardest things to do is, in chemistry, we have to go from this macroscopic world that we interact with, that we touch, taste, feel, see, smell, to something that's even smaller than our best microscopes can see. The submicroscopic realm. If I got out a light microscope from biology, I wouldn't be able to see atoms or compounds. So we kind of have to use our imagination a little bit. So we use these different representations. Here we have the formula representation, which is, as I said, is great. It tells us that there's 2 hydrogens and 1 oxygen. But we can also represent these as a ball and stick, where atoms are the balls and the stick represents the bond. Now, this is great because it actually tells us one other bit of information that H2O doesn't tell us. This shows us shape as well. The shape of molecules is actually very important in terms of their reactivity. But that's not actually as good as it should be. Because that ball and stick representation, it's showing a bond as being this stick that is holding these atoms together, and that's not true. It's actually an overlap of electrons in the atoms. So that's where we have this space fill representation. The space fill also shows us the shape, but it's a lot harder to draw. Okay? All of these are equivalent representations for water. Now, different elements are represented by different colors in general. As I said today, these are actually the ones you really kind of got to know. Is carbon's black, hydrogen's white, oxygen's red, nitrogen is blue. All the other ones here, they're up for debate. Okay? If you're going through the book and you're like, well, what is that supposed to be? I don't know what atom that is. Come back to this picture and figure it out. Okay? You don't have to memorize it. There's not going to be any sort of test on the colors or anything like that. It's just, in general, these are the coloration we use. Now, all matter is composed of the same building blocks called atoms. And these atoms consist of three smaller particles or subatomic particles: the proton, the neutron, and the electron. The proton has a positive charge, the electron has a negative charge, and the neutron has no charge. Now, if you take a look at the masses of these particles, the mass of the proton and the neutron are essentially the same, 1.67 times 10 to the minus 24 grams. But the electron, 9.1 times 10 to the negative 28th grams, is approximately 2,000 times smaller than the proton. Which means the mass is actually pretty much negligible. No atom has 2,000 electrons. So the electron really doesn't make up any mass of the atom. Now we have the atomic mass unit. This is used to make the masses of our elements easier to work with. Okay, so we don't have to worry about the number of grams. So the proton and the neutron have roughly the same mass in AMUs, and that's 1. And as I said, the electron basically has a negligible mass. The structure of the atom is that the neutron and protons are stuck in the nucleus, okay? And then this is a dense core of the atom. That's where the mass of the atom really is going to lie, okay? And the electrons are actually on the outside in this electron cloud. And this comprises most of the volume of the atom, is this cloud. Now what this cloud is kind of weird. It is what we would call a probability density function, which is a fancy way of saying we might find an electron in this volume. Okay? The electrons are zipping around doing their thing. Okay? So it's not really like the old high school representation of the atom where we had the nucleus and we put electrons on the outside like this, and they'd just be these concentric circles, and that's not how it works. Okay? It is this electron cloud. Now, representatively, the size of the average nucleus is about 10 to the minus 15 meters, whereas the size of the atom is about 10 to the minus 10 meters. Okay? That is a really big difference. To kind of put this into perspective, if I could blow up this nucleus to the size of a normal little green pea, the nearest electron would be a mile away. In other words, it's really, really tiny for the nucleus, and the volume of that atom is so much larger that the nearest electron would be a long ways away. Okay? And what's in that space between the nucleus and the electron? Nothing. Nothingness. Okay? Which is kind of intriguing, and if you really want to get into it, my Chem 120, I go into this in depth, but it's really kind of creepy if you think about it. So I try not to think about it too hard too often. But suffice to say that most of the atom size is taken up by this electron cloud. It's the electrons that are on the outside. It's the electrons that show us or allow us to have chemistry. Now, just as a little reminder, opposites attract. Opposite charges attract, while like charges repel. So, 2 protons are going to repel each other, 2 electrons are going to repel each other, but a proton is going to be attracted to an electron. A neutron's not going to do anything. It's going to sit there and go, yeah, I'm here. So, it is the opposite charges of the proton and the electron that allow atoms to exist. So, from the periodic table, the atomic number that we saw at the top of each of these elements that we talked about earlier is given the letter Z as a symbol, okay? And this is the number of protons in the nucleus. So if you're a lithium atom, you've got 3 protons. If you're a hydrogen atom, you've got 1 proton. If you are a krypton atom, you've got 36 protons, okay? Every atom of a given element is going to have the same number of protons. If I've got 3 protons, I'm lithium. If I've got 4 protons, I'm not lithium. Okay, I'm beryllium. Because different elements have different atomic numbers. And a neutral atom is going to have no net overall charge. In other words, for all the positives that we have, we're going to have all the negatives. So if the number of protons is 3, then for a neutral atom, the number of protons has to equal the number of electrons, so we'd have 3 electrons. Now, what about those neutrons? Well, that's where isotopes come in. Isotopes are atoms with the same element that have a differing number of neutrons. So we define the mass number, given the letter A, as the total number, or the sum, of the number of protons, or Z, plus the number of neutrons in an atom. Okay? And that makes sense since the mass of the atom is defined by the number of protons and neutrons, because they're about the same size. So we can write an isotope symbol like this, where the mass number is given as a superscript to the left side, the atomic number is given as a subscript to the right side, and we write the element symbol. Now, the atomic number tells us the number of protons, so in this case we've got 17 protons. And if it is a neutral atom, we are going to have 17 electrons. But the number of neutrons is not going to be 17, nor is it going to be 35. It's going to be this number, this mass number, the sum total of protons and neutrons, minus the number of protons. So the way we write these, we kind of set it up so that we get 35, 17. We can do a subtraction right here to get 18 neutrons. So here we have 3 different isotopes of hydrogen. Hydrogen with a mass number of 3, hydrogen with a mass number of 2, and hydrogen with a mass number of 1. So how many protons are present in each of these? Well, it's hydrogen. The lower number is the number of protons, so there's 1 proton in each of these. What about the number of electrons? Well, if it's a neutral atom, the number of electrons must equal the number of protons, so each one of these has got 1 electron. But what about the number of neutrons? I take this top number minus this bottom number, the mass number minus the atomic number. So 3 minus 1 is equal to 2 neutrons. 2 minus 1 equals 1 neutron. And 1 minus 1 equals no neutrons. So the lightest element known in the universe is a hydrogen atom with no neutrons. It's just a proton and an electron. Now, if you look at a periodic table, they don't give you the mass numbers. What they give us is this number at the bottom that doesn't look like a mass number. The mass numbers are whole numbers. But these weights at the bottom, these atomic weights, given in atomic mass units, are a weighted average of the masses of each of the naturally occurring isotopes of a particular element. Okay? So, the periodic table, in general, atomic number, symbol, weight. So how do we calculate the atomic weight, or the atomic mass, of an element? So what is the atomic weight of chlorine? So the way we do this is we list out each isotope's atomic mass units and its abundance in nature. How often does it occur? This isotopic abundance, or natural abundance, tells us how often each of these elements occurs in nature. So chlorine with a mass number of 35 is 75% of the time what you're going to find. Chlorine with a mass number of 37 makes up about 25% of what you're going to find. Now, these masses in AMUs are not exactly the same as their mass numbers. Okay, you notice they're close. Don't worry about it. Mass numbers would be given to you as well as isotopic abundances to find the atomic mass. So what we're going to do is we're going to take each of these mass numbers and multiply by their percent abundance as a decimal. Okay? So how did I get that decimal? I took this number and divided by 100 because it's a percentage. That's what percent means, per 100. So 75.78 divided by 100 gives me 0.7578. 24.22 divided by 100 gives me 0.2422. So when I take these mass numbers, or these masses, times their percentages, I get 26.5003 AMUs and 8.9541 AMUs, and I add them together. Okay? This is how you do a weighted average. Now, I'm going to round this to 4 sig figs because I had 4 sig figs in my starting position. So 35.45 AMUs. Now, if you take a look at the periodic table, you'll see that it has 35.453 AMUs written for chlorine. Now, why do they have an extra number? They had better data than what we worked with. All right, let's go over basic features of the periodic table. As we've already seen, a row is called a period and a column is called a group or a family. Now, we have the main group elements. These are the tall columns on the right and left side of the periodic table, and they get the numbering scheme 1 through 8A. The transition metals are the ones in the center, and they get a numbering 1 through 8B. The inner transitions are the guys that are at the bottom of the periodic table. Now, they're the lanthanides and the actinides, and they have no group numbers assigned to them. They are fascinating atoms, but they don't really fit the periodic table scheme. So just keep that in mind. So we have the period numbers here, 1 through 7, and our group numbers, like 2A and 3B. So main group elements, transition elements. Now, some of these groups or families are going to have names that you're going to need to know, okay? And each element in a group is going to have similar chemical properties. The reason for that is they're in the same family. It turns out that elements in the same family are actually going to have the same number of electrons in their outer portion of the atom that the world sees. So the world sees these electrons, that's where the chemistry comes in, and they have the same number of those electrons on the outside, so they behave very similarly. So group 1A are called the alkali metals. Alkali metals. As I said, you do need to know these. Group 2A are known as the alkaline earth elements or alkaline earth metals. They are soft, they are shiny, they have low melting points, they're good conductors, and they react with water to form basic solutions. What is a basic solution? It's the opposite of an acid. Okay? These guys are never found in nature as their element. The reason for that is they react with water. If you had a mine for sodium, as soon as any water got down there, it would react to form a basic solution. It wouldn't be sodium metal anymore. So, never found in nature. Group 7A are known as the halogens. Okay? They are very reactive, and they exist as two atoms joined together. Okay? Let's talk about that real quick for just a second. And that is what we would call diatomic elements. Okay? All of the halogens are diatomics. There are actually 7 diatomic elements. And you do need to know these, because in nature, these elements never exist as their single atoms. They always exist as these 2 atom pairs. They're hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. H2, N2, O2, F2, Cl2, Br2, I2. 7 diatomic elements. All of the last ones here, from fluorine down to iodine, those are our halogens. Now, they're very reactive. Chlorine gas, Cl2, was actually the first modern chemical warfare weapon deployed on the battlefield in 1917. What it does is it causes burns in your respiratory tract, and you basically drown in your own fluid. So, pretty nasty stuff. Now, contrast that with Group 8A. These are the noble gases. They're really very stable. They don't do much. They rarely combine with other elements. That doesn't mean we can't make them combine. We have, but it's not an easy task. It usually requires some very special experimental conditions. Carbon is an odd duck. Carbon has the ability to join with itself, what we call catenate. And when it joins with itself and other elements, it can form long chains or rings. And that's very, very versatile, and it does things that we don't see on the rest of the periodic table. Okay? Now, there are 3 versions of carbon-only structures. These are what we would call allotropes. Okay? Allotropes are different arrangements of atoms for an element. Okay? So the first one we have is diamond. We all know diamonds are very, very strong, very, very hard, and they're very, very compact. Maybe I should change colors so that you can actually see that. If you take a look, these are actually forming a 3-dimensional array of 4 carbons surrounding each other carbon. Okay? That is a very strong sort of system. Okay? And it leads to the strength of diamond. Graphite, however, consists of these 6-membered rings in sheets. Okay? And those sheets sit on top of each other. And so they just sort of like layer like this. Now, graphite is what we use in pencils. And the reason it works is what you do is, as you're writing, you just start shearing off these different layers. And that's what's left behind as you're writing. Now, the third one is Buckminster fullerene, or buckyballs. Yes, that is a real term, buckyballs. Now, buckyballs are kind of interesting. They're a newer form of carbon, discovered in the early 70s, late 60s. But what we have with a buckyball is we've got a 5-membered carbon ring surrounded by 6-membered carbon rings. And if that pattern sort of looks familiar, it should. It's a soccer ball. Buckyballs are shaped like soccer balls. Okay? Now, they have some interesting electrical and mechanical properties that we don't see in graphite or diamond. But I'm not going to get too far into it. So, allotropes, the same atoms but different structures. Another allotrope that you might be familiar with, we breathe oxygen, O2, but we have ozone, O3, as a layer above our Earth, protecting us from harmful rays. So oxygen versus ozone. These two are allotropes. Alright, so let's talk about electronic structure, because the electron is really what gives an atom its chemistry. It's because that's what the world sees. It doesn't see the nucleus. The nucleus is in the center, and it's really, really tiny. Alright, so electrons are confined to a specific area around the nucleus. Okay? This means that the electron is going to have a certain particular energy. Okay? I know that sounds kind of weird, but it is weird. It is weird. There's no way around it. It is weird. But it's kind of cool, too. So I'm going to try to make this as painless as possible. But those specific energy levels are called principal energy levels, or shells. And they get the symbol N. And the shells are numbered as integers. 1, 2, 3, 4, 5, 6, so on and so forth. Okay? The lower the value of N, the closer they are to the nucleus, and the lower in energy they are. Okay, so N equals 1 is the closest you can get to the nucleus, and it's the lowest energy level. Higher energy levels are further from the nucleus and are higher in energy. So an electron confined in shell 3 is going to have more energy and be farther away than an electron confined in shell 1. Okay? Now, the further away you are from the nucleus, the more electrons you can hold. So the larger numbers of N hold more electrons. So this is how this works. If my nucleus is here, my first shell is there, that can hold 2 total electrons. Shell 2 is here, farther away from the nucleus, that can hold a total of 8 electrons. Shell 3, even farther away, that can hold 18 electrons. And shell 4, 32 electrons. So there's an increasing number of electrons with increasing energy with an increasing number of N. Now, each of these shells are divided into subshells. Okay? So each of these energy levels are divided up into smaller parts. And these are identified by the letters S, P, D, and F. S, P, D, and F. Okay? Why S, P, D, and F? It's a great question. It has to do with the way light interacts with matter. Okay? S, P, D, and F stands for simple, principal, diffuse, and fundamental, if I remember correctly. They're letters that have stuck. Okay? Now, each of these subshells consists of orbitals. Okay? This is different than the orbit that we had talked about prior, when I said that that grade school notion of here's our nucleus and then we've got circles around it. That's not true. Okay? Orbitals are orbit-like. What it is it's a region of space where there's a high probability of finding an electron. Okay? Now, each of these orbitals can hold 2 electrons. In the S subshell, there is 1 orbital. That means the S subshell can hold 2 electrons. The P subshell contains 3 orbitals. Now, each of those orbitals can hold 2 electrons. So 3 orbitals times 2 electrons each equals 6 electrons. Ds have 5 orbitals, so that can hold a total of 10 electrons. Fs have 7, or 14 electrons as a capacity. So for energy levels 1 through 4, we have our N level, our shell level, and the orbitals that sit in that shell. So, the very first orbital in every atom is the 1s orbital. It can hold a maximum of 2 electrons. In shell number 2, I start off with an s orbital, which can hold 2 electrons. Then there are 3 individual p orbitals, which can hold a total of 2 electrons each, but since there are 3 of them, we get 6 total electrons, which gives us 2 plus 6 gives me an 8 total electrons for energy level 2. Energy level 3, we start off with an s, we get 3 p's and 5 d orbitals. So 2 plus 6 plus 10 means 18 total electrons. That matches up with what we had before, where we were seeing the total number of electrons per shell. 4, we have the 4s, 3 4p's, 5 4d's, and 7 4f's, for a total of 32 electrons. Now, each orbital has got a specific shape. You need to recognize the shapes of these orbitals. All s orbitals are spherically symmetrical, okay? They're like little spheres, okay? All p orbitals have dumbbell shapes. So this is what we call the dumbbell shape, okay? Now, remember, how many p orbitals do I get? I get 3 of them. So this is the 2px, the 2py, and the 2pz. This is just based on the direction they're pointing. And if I draw all of those 3 orbitals on the same set of axes, notice they're all 90 degrees from each other, and they just kind of form a bumpy sphere. D orbitals look even funnier than that, and F orbitals are wacky looking. But all it comes down to is, at the end, when we put all these orbitals together on each atom, they just come out to look like a sphere. Maybe a bumpy sphere, but a sphere nonetheless. So, now we're going to answer one of the fundamental questions, I think, in all of chemistry. I think all of chemistry can be brought down to 3 fundamental questions. The first one being, where are the electrons and what are they doing? The second is, what shape is it? And third is, does it act as an acid or a base? Okay? If you can answer those 3 questions, you get a pretty good handle on the chemistry of a particular compound. So, let's talk about where are the electrons and what are they doing. That is the electron configuration when we're talking about atoms. Electron configurations show how all of the electrons are arranged in an atom's orbital. Now, the lowest energy arrangement is what we call the ground state. Any state or any sort of configuration that is not at the lowest energy would be what we would call an excited state, not with the lowest energy. Okay? So, the rules to determine the ground state are we place electrons in the lowest energy first, and then we fill in terms of increasing energy. So the very first orbital is the 1s orbital. We fill up the 1s orbital, then we move to the next highest energy level, which would be 2. We fill up the s orbital there. Now, if we follow this through, we start off with the 1s, then we go to the 2s, and then the 2p. Okay? Then we move to the 3s, and then the 3p. But take a look, this pesky 4s here is actually lower in energy than the 3d. So the 4s orbital gets filled before the 3d. You fill up the 4s, we fill the 3d, and then we move to the 4p. But then this pesky 5s is lower in energy than the 4d, so we fill it up first, then we go to the 4d, Then we get the pesky 5p, and even peskier, the 6s, before we come back and fill up the 4f, the 5d, the 6p, we get the 7s, before we come back and fill up the rest. Okay, now that's confusing. It's okay. We have a way around that. We can draw an Aufbau diagram. What is an Aufbau diagram, you ask? Well, an Aufbau is German for filling up. Okay? And so the Aufbau diagram is pretty simple, and it's going to help us to understand how this orbital filling goes. So, to recreate your own Aufbau diagram, you're going to write the number 1, and then you're going to write the number 2 underneath it, 3, 4, 5, 6, and 7. Next to those, you're going to write the letter S. Now you're going to move over 1, and you're going to write 2, 3, 4, 5, 6, 7. And next to those, you're going to write the letter P. Move over 1, 3, 4, 5, 6, 7. And write the letter D. And then move over 1, 4, 5, 6, 7. And you're going to write the letter F. Okay? Now here's the hard part. You're going to draw an arrow at 45 degrees through the 1S. Then you're going to draw an arrow 45 degrees through the 2S. Then the 2P. Now you'll notice after you go to 2P, it'll go to the 3S. Then we're going to do 3P through the 4S. 3D through the 4P through the 5S. 4D, 5P, 6S. 4F, 5D, 6P, 7S. 5F, 6D, 7P. 6F, 7D, and finally 7F. Now, you'll notice that if you do this correctly, these guys are about equally spaced. Okay? And that's what we want, is we want them to be equally spaced, and we want it to look like that. The way we use this is we start from the tail and we go to the tip. So if I'm filling up orbitals, I'm going to fill up the 1s first. Once I'm done there, I go back to the tail and then down to the tip. So then, after the 1s, we had the 2s. That's higher in energy. Then we go back to the tail and we would do the 2p and then the 3s. Then we would do 3p, but then we'd have that pesky 4s before we come back and fill the 3d. So if you follow this through, this will match up perfectly with the diagram on the previous slide. So we're going to use this Aufbau diagram to help us fill up atoms' electron configurations. So rule 1 was lowest energy first to highest energy. Rule 2 is each orbital can hold a max of 2 electrons. Okay? Rule 3 is when orbitals are equal in energy, we add 1 electron to each orbital until everything is half filled. Once I've half filled everybody, then I can completely fill them, or come back to completely fill them. Okay? The way I write that, or the way I say that often, is we half fill before pairing. Now there are multiple ways that we can show electron configurations. The first we're going to use is an orbital diagram or a box diagram. Box diagrams show orbitals as, well, you guessed it, boxes. Electrons are shown as arrows. Okay? Now, if I have two electrons in an orbital, they must have paired spins or opposite spins to fit in the same orbital. Okay? The reason behind that has to do with the fact that electrons are negatively charged. Okay? If electrons are negatively charged, they're going to repel each other. In order to make them fit in the right way, they have to be spinning opposite directions. Okay? Now, one thing I want to note is whenever I do a box diagram, I actually don't write a box. I just draw a single line. Okay? So don't freak out that I'm not drawing an entire box. It's just drawing a box takes forever. So here we have box diagrams and electron configurations for the first row elements in period 1. So they are hydrogen, which has got one electron. That one electron is going to go into that 1s orbital. Okay? Now we can shorthand this as writing 1s1. In other words, this is the energy level or the n value. This is the orbital. And that is the number of electrons present. Helium has 2 electrons, so our box diagram looks like this, where they are oppositely spin. Okay, they have to have opposite spins. And our electron configuration would be 1s2. For the second row elements, period 2, let's do lithium. So first I fill up the 1s. Then I can fill up the 2s. Okay? Now I've only got 3 electrons to place, so I don't actually fill up the 2s. So 1s2, 2s1 would be my electron configuration. Now carbon has got 6 electrons. We start off with the 1s, then we fill up the 2s. After the 2s, following our Aufbau diagram, we end up with the 2p. Now notice in our box diagram here, the 2p, we're going to half fill the orbitals, because remember there are 3 p orbitals. We're going to half fill those guys prior to pairing them up. So we put 1 electron in this one, 1 electron in this one, and we ran out of electrons. Now in our electron configuration, we show 2p2. Now that's one of the drawbacks behind the electron configuration. While it is shorter to write, and you don't have to draw boxes, it doesn't show us that those p electrons are actually in separate orbitals, which is kind of a nice thing to have sometimes. Now if I do neon, that's 10 electrons. I fill up the 1s, I fill up the 2s. I would half fill the 2p's before I came back and paired them up. So 1s2, 2s2, 2p6. Now notice, with this is not saying that there are 6 electrons in a single p orbital. We have to remember that we've got 3 p orbitals, each holding 2 electrons. We can shorten the electron configuration using what we call the noble gas notation. Okay? And the way this works is we take the symbol of the previous noble gas and add the additional electrons. So for carbon, the noble gas that was prior to it was helium. Well, helium has an electron configuration of 1s2. So really, that and that are the same thing. So I can put helium symbol in brackets and then fill out with the rest of the electrons. Helium 2s2, 2p2. Wow, that is not really a shorthand for that. But for other elements, it is quite a shorthand. Okay? So let's do an electron configuration. I'm going to give you an Aufbau diagram and an element to do. Let's pick something like bromine. Bromine has 35 protons. That means that an element of bromine, or an atom of bromine, is going to also have 35 electrons. So, to do the symbol notation, remember we start with the tail and go to the tip. So I would have 1s, I can put 2 electrons in there. After the 1s, I go back up to the 0 and I fill up the 2s. 2s, I can put 2 in there. After 2s, I go to 2p. 2p, remember, can hold a total of 6. After 2p, 3s, that can hold a total of 2. Then 3p can hold a total of 6. After 3p, I go to 4s. I can hold a total of 2. After 4s, I go to 3d. Ds can hold 10 electrons total because there's 5 orbitals. So 3d10. After 3d, I go to 4p. Now, the p's can hold 6, but I only need 5. If you count this up, 2, 4, 10, 12, 18, 20, 35. There is my standard electron configuration notation. Okay? Now, if I take a look at the noble gas prior to bromine, the noble gas prior to bromine is argon. Argon has 18 electrons. So what I can do is go 2, 4, 10, 12, 18. All of these electrons are the same as argon. So I can write argon in brackets and then fill with the rest of these guys. 4s2, 3d10, 4p5. That is a much shorter electron configuration. So, let's do something a little bit easier. Calcium, 20 electrons. Okay? Its electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, the noble gas prior to calcium is also argon, which means that all of these electrons are like argon. So, the noble gas notation is argon 4s2. Much, much smaller. Also, it turns out that if I have a periodic table, I don't necessarily need the Aufbau diagram because I can use the structure of the periodic table to determine my electron configuration. It turns out that this law of periodicity, because it's about the electrons, actually lends itself to the electron configurations. So what we get are blocks. We have 4 blocks. The S block, which is in blue. You'll notice this comprises group 1 and 2A, and also helium. Okay, helium's kind of a lone guy out. So groups 1 and 2A. We have the D block, which are all of our transition metals. We have the P block, which is the remainder of our main group elements. And then we have the F block, which is our intertransition metals. Every time I say D block and F block, I always think of this as like prison. This is electron prison. You have to be able to tell those electrons what blocks they're going to go into. Okay? So, how do we use these blocks? Well, number one, you have to memorize the blocks. That's the first thing. You have to remember where they're at. The S block, the P block, the D block, and the F block. The second thing you have to notice is kind of funny. Notice that in the S block, period 1 is 1s. Period 2 is 2s. 3, 3s. 4, 4s. 5, 5s. 6, 6s. 7, 7s. You should also notice that in the P's, 2p, 3p, 4p, 5p, 6p, 7p. In terms of the S and P, this is the period number. Okay? But when we go to the D block starts in period 4. So the D block is period -1. And the F block is actually period -2. So the F block starts in period 6. Okay? That's the first thing. The second thing is you have to be able to count. All right, so here we have that periodic table with a couple of elements pasted in here so that we can see what we're doing. Okay? So, as I said, we don't really need the Aufbau diagram if we have a periodic table and we memorize our groups or our blocks. So, let's do chlorine. Chlorine has 17 electrons. Okay? Now, I can start counting out from hydrogen. The 1s, there are two of them. 2s1, 2s2. After that, I go to 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Then I go to the 3s, 3s2, 1, 3s2. Then 3p1, 3p2, 3p3, 3p4, 3p5. And there I am at chlorine. That should be 2, 4, 10, 12, 17 electrons. Look at that. Pretty easy to remember. Okay? It's also easy to use the noble gas configuration because I just look to the noble gas prior, which is neon here, and I write Ne in brackets, and then I start at the 3. 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5. Let's do bromine, because we've already seen bromine. Now I'm not even going to put out how many electrons bromine has, because all I have to do is just follow the noble gas configuration. So argon is the noble gas prior to bromine. So argon in brackets, 4s1, 4s2. Now, here's where it gets funky because I go to the 3Ds. 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. And then back up to our 4Ps. 4P1, 4P2, 4P3, 4P4, 4P5. Now, that is pretty easy, okay? It just requires you to count and to memorize those blocks, okay? Now, there are some funky things that happen, and I do want to point out a couple of funky electron configurations. So we're going to look at chromium and copper, okay? Chromium has got 24 electrons. Now, we would expect that if I just followed through, we'll do the noble gas configuration. I'm starting off at argon, and then I would go 4s2, then 3d1, 3d2, 3d3, 3d4. But it actually turns out that reality says argon, 4s1, 3d5. Okay? The reason for that is this is now half filled. Okay? Because remember there are 5 d orbitals. So we've now filled up that, we've half filled that orbital. Half filled, half filled. Another way that we can state that rule that I said is half filled orbitals before pairing. We can state that as orbitals energies are minimized when spin is maximized. Okay? And by spin I mean the direction of those electrons. If they're all up or all down, that's going to maximize your energy. Having some up, some down, and some up is more energy than if they're all half filled and of the same spin. Okay? Now with copper, we might think with 29 electrons, argon, 4s2, 3d9, but much in the same way, reality gives us argon 4s1 3d10. That's because we filled the third energy level. Okay? So those are two to watch out for. They may pop up. Okay? So they don't quite follow the rules. I'm never going to ask you the F ones because they really don't follow the rules. There's all sorts of weird things that happen with the F block. Okay? Alright, now that we've got the electron configurations down, let's talk about what electrons are seen by the universe, by the world. Because it's the chemical properties of those outer electrons that are of importance. This is what we would call the valence shell. The valence shell is the outermost shell, or the highest value of N. Okay? We call those electrons valence electrons. So, the key to finding out the valence electrons is you look for all of the electrons with the highest value of N, the highest number present in your electron configuration. So for chlorine, the highest number is 3. So there are 2 in the S and 5 in the P, so the total number of valence electrons is 7. And we would say the valence shell is N is equal to 3. For beryllium, the valence shell would be 2, and there would only be 2 valence electrons. So you could write out the valence, or write out all the electron configuration, and then just figure out who's got the highest number and add up all those electrons. But it turns out that elements in the same group have similar electron configurations. Okay? And elements in the same group have the same number of valence electrons. And the even more fun part about this is for our main group elements, remember our A's, group 1A through 8A, the number of the column is the same as the number of valence electrons, except for helium, which has only got 2. Okay, that's the odd man out. This is because, as we've talked about, the chemical properties of a group are very similar. They have the same electron, or similar electron configurations, but they have the same number of valence electrons. So, group number 1, 1A, hydrogen has 1 valence electron, lithium has 1 valence electron, sodium has 1 valence electron, and it is in the shell of whatever period it is in. So, if you're in group 2A, you have 2 valence electrons. 2 valence electrons. If you're in 3A, you've got 3 valence electrons. 4A, 4 valence electrons. 5A, 5, 6, 7, and so on. 8 and 8. So if I asked you, how many valence electrons does selenium have? Se. Well, you would find Se on the periodic table, and if you do that, you would see it is underneath sulfur. Well, sulfur is in group 6A, so the number of valence electrons on selenium is 6. How many valence electrons does iodine have? Well, it's a halogen. It's in group 7A. Therefore, it's got 7. Now, this leads us to another way of representing atoms and their electrons. We can use electron dot symbols, or what we're going to later call Lewis symbols. Okay? Lewis symbols and Lewis structures are a way for us to show how atoms are connected based on their electron configurations. Now, we're going to start off really simply by just doing electron or Lewis symbols for atoms. Okay? So, this works by using dots representing valence electrons placed on the top, bottom, or sides of an element symbol. Each dot represents 1 valence electron. Okay? Now, the way we do this is we follow the same rules as we followed before. Okay? So here it shows you for hydrogen, carbon, or oxygen. I'm going to just make this a little bit different. So for helium, Okay? Helium has 2 valence electrons. Helium, I would actually draw the 2 dots on the same side. Okay? They're paired because remember, it's 1s2. Now, let's do lithium. Lithium's got 3 electrons, but only 1 valence electron. So I would put a single dot next to it. Beryllium is in the alkaline earth metals. It's got 2 valence electrons. I would actually separate those, okay? Well, I know that it's technically the 2s2, that's the valence electrons. They would be paired. I'm not going to do that, okay? The only one that I pair it up for is helium. If I move to boron, which is in group 3, I would have 3 electrons. Carbon, 4 electrons. Okay? So now I've used up all 4 sides. All 4 sides are used up. So when I go to nitrogen, I'm going to half fill my electrons, but I've got 5 valence electrons. I'm going to half fill, and then I'm going to start to pair. So it says, with greater than 4 valence electrons, we start to pair. Okay? So oxygen, you can see, the way I would draw oxygen, I would draw 1, 2, 3, 4. Oh, now I got to pair them up. 5, 6. Now, you go, well, wait a second, Dr. Brinkley, that does not look like that one. It doesn't matter where the dots are as long as they are on the top, bottom, and sides. We try to keep them to just the top, bottom, and sides. Okay? All right, the last 2 concepts that we're going to talk about are periodic trends. And these are trends in atomic size and in ionization energy. Okay? So, atomic size. This is a periodic trend, which means if I look at the periodic table and I locate elements, I can tell relative sizes of the atoms just based on where they're at. So, atomic size increases as you... Oops. I don't like the way they draw this. I always draw it differently. So, let me just shrink this down a little bit and draw the way I draw it. I draw my crappy periodic table, and I go, atomic size increases as you go down, and atomic size decreases as you go across. Okay? Now, it's kind of a weird situation as to why this happens, but just say this. It is this way because it is this way. Okay? The atomic size going up as you go down a family is pretty simple to explain because of the value of n. We remember the value of n, the bigger the value of n, the farther away the electrons are from the nucleus. Therefore, the bigger the atom. But as you go across a period, the size decreases. And that's kind of a weird why, but the reason is the protons can actually attract the electrons more readily going across than they can going down. Okay? So atomic size decreases as you go across a period, and it increases as you go down a family. Now, ionization energy is the amount of energy needed to remove an electron from a gaseous atom or ion. Okay? I'm going to change the definition there just a little bit. The amount of energy required to remove an electron from a gaseous atom or ion. Now, ionization energy decrease as you go down a column. Okay? And they increase as you go across a family. If you notice, this is the exact opposite of atomic size. Atomic size increases as you go down, and it decreases as you go across. This is just the opposite. And the reason for it being the opposite has to do with the way atomic size works. It's easier to steal an electron if it's farther away. That's why ionization energy decreases as you go down. And it's harder to steal an electron that's closer to the nucleus. That's why it increases as you go across. Now, I'm going to add one more periodic trend that I don't believe is in the book, but I like it. And that is electron affinity. Okay? Ionization energy is the amount of energy required to remove an electron. Electron affinity is the amount of energy change when you add an electron to a gaseous atom or ion. Okay? And the trend for electron affinity is this. As you go down, electron affinity decreases. As you go across, electron affinity increases. The reason for this is the same sort of reasoning. It is the opposite trend of atomic size. So guess what? If you memorize atomic size, you know the trends in electron affinity and ionization energy by reversing it. Okay? If you've got a bunch of electrons, you don't really care if somebody adds an electron. That's why electron affinity goes down. If you don't have many, you're really happy to get one. So, the atoms at the top that don't have many electrons are happy to receive an electron. The ones that are at the bottom don't really care. Now, over here, on this side, those atoms are holding those electrons that are in the outer shell a little bit more closely. That's why atomic size decreases. Well, if you're a close-knit family and you have one more baby, you're going to love that baby. Okay? You're going to hold it close. That's what I say about this, is it's kind of like holding your family close. The closer you are to your family, the closer you're going to stay together. And electron affinity is kind of like loving on your family members. Okay? So the trends for ionization energy and electron affinity are opposite that of atomic size. So if you memorize the trend in atomic size, you'll know the trend in electron affinity and the trend in ionization energy. And that concludes Chapter 2.